Dear students, so in this video we can discuss the Miller indices. A small description of that is you have studied in a degree class. Now we have certain terms related with that. The first one is a site or a rational. It is the geometrical features of a crystal which are represented by lattice points. That is also known as a rational or site. Then rational point, a lattice point with respect to another lattice point is a rational point, we can call them. Then rational line is a row of lattice point is known as a rational line, and rational plane is a plane defined by lattice points. These are, now we can represent certain indices to represent this site. Then this the position of any lattice point. Suppose we have a lattice point here. Then the position of any lattice point related to a chosen origin is defined by three of its coordinates x, y, z, and the coordinates are expressed in the following forms. So you can express the we have the crystal translation vectors are here. Then coordinates are there x, y, z, and this coordinates x is related with m into a, y is equal to nb, z is equal to pc, where abc are the lattice parameters and m, n, and p are integers, and these numbers are termed as the site indices and are written in the form double bracket m and p. So you have to note this form of bracket. So here if it is a double bracket, it indicates the site indices. Then another one is the indices of direction. We have a straight line passing through the origin is chosen. We have chosen. It is defined by the indices of the first lattice site or point through which the line passes. In order to represent the direction, first of all we are taking a straight line which is passing through the origin. First of all we consider an origin and a straight line is drawn. Then a straight line is drawn through it, and we are taking the indices of the first lattice site, and that through which the line passes. We can take a line from this origin. Suppose it passes along this this direction. Okay, so this is the origin, so you can draw a line here. So this is the first lattice point. This is the first lattice point through which the straight line passes. So indices of that lattice point is the indices of direction. That is, indices of direction is defined by the three smallest integers that describe the position of the site nearest to the origin which lies on the given direction. A particular direction origin straight line first വരുന്ന lattice point അല്ലെങ്കിൽ സൈറ്റിന്റെ ഇൻഡിസസിനെയാണ് നമ്മൾ ഡയറക്ഷൻ ഇൻഡിസസ് അല്ലെങ്കിൽ indices of direction എന്ന് പറയുന്നത്. Site indices are the same as indices of direction. So both will be the same because we have taken the same origin. Then the steps to find out. Now the steps to find out the indices of direction. First of all, note down the coordinates of the lattice site nearest to the origin in a given direction. First of all, you have to find out the coordinates of the lattice site nearest to the origin in a given direction. Divide the coordinates by an appropriate unit translations. If fractions result, multiply each of them by smallest common divisor. Put the resulting integers in a set of square bracket HKL to get the required indices of that and all parallel directions. So similar to the type we have already studied in the Miller indices, here we are taking the dividing it with the translation vectors, and then if fractions are resulting, then we will multiply with the common divisor, then we will put in a double square bracket to get the direction indices of the direction. And all the planes, that is important, to get the required all parallel directions have the same indices of direction. Then equivalent direction, there are these are the sets of direction having identical spacing between the item, that is same unit translation called the equivalent directions. Equivalent directions are the sets of directions having identical spacing between the atoms. That is same unit translations, and which are called the equivalent translation. The shortened notation used to specify a family of direction is a set of angled brackets. If it is enclosed in an angled bracket HKL, it will indicate a family of direction. So 100 consists consists of directions 100 bar 100 010 01 bar 0 001 001 bar etc. All these can be put in this this family of directions. Then indices of lattice planes. So we have studied two types of indices. One is the site indices, and they are the same as the indices of direction. If it is a site indices, it is represented in double bracket. If it is a double square bracket, if it is in a single square bracket, it is a direction of that is indices of direction. Then we have next is the indices of lattice plane. A crystal lattice may be considered as an assembly of number of equidistant parallel planes passing through the lattice points and are called lattice planes. A crystal lattice as a whole, you can consider several lattice points, and each lattice points can be associated with a lattice plane. So it is an association of several lattice planes. Equidistant parallel planes are passing through the lattice points we can consider. And in order to represent the lattice planes, we are using certain indices, and the one of the indices used to represent these lattice planes are the Miller indices. First of all, in order to find out the Miller indices, we have the following steps. To find the orientation of planes in the crystal, Miller indices are used and are written as HKL, and these steps are then determine the intercepts of the plane along XYZ axis in terms of lattice parameters. First of all, you have to determine the intercepts of each plane along with the three mutually perpendicular direction, and then second step, divide these intercepts by the appropriate unit translations A, B, C, etc. Not their reciprocals. We have to take the reciprocals of that one. Here, if fraction result, multiply each one by the smallest common divisor. Here there is no, in the case of direction, we have unit translate, there is no reciprocal is taken, but here we have to take the reciprocal. Then if fraction result, multiply each of them by the smallest common divisor, then put the resulting integers in parentheses HKL to get the required Miller indices of that and all parallel. So all parallel planes have the same Miller indices. So in a crystal, a plane cards, as an example, we can look into an example. We have a plane cards intercepts 2A, 3B, 4, 6C along the crystallographic axis. Determine the Miller indices of that plane. So here we are, first of all, we are dividing to this with the division by unit translation. 2A by A, that is equal to 2. Here not 2, it is A. Then 3B by B, 3, 6C by C, that is 6. Then we are taking the reciprocals. Then we have the common divisor, that is we have taken it as 6. So here it becomes 3, 2, 1, and they are enclosed in this parenthesis. That is 3, 2, 1 is the Miller indices of the plane corresponding to that. And the direction 3, 2, 1. If we have put this 3, 2, 1 in a square bracket, then this plane will be perpendicular to that direction. So another example, a plane parallel to x-axis and cut intercepts of 2.5 respectively along y and z axis. So here it is parallel to x-axis means its intercept is infinity. Then 2a half c, so infinity by a, that is infinity again. Here 2, here we have 1 by 2. Then we have to take the reciprocal. So 1 by infinity equal to 0. So 0 half half. 0 half 2, then we have multiplying with the 2, you will get here 0 1, then here 4. So 0 1 4 is the representation of the lattice. So any plane which is parallel to a particular axis will have the Miller indices 0 here. So 0 means it is parallel to that particular axis. Then we can represent certain planes. 1 0 0 plane of a cubic crystal. So here H1 is equal to 1, K and 0, L is equal to 0. So that is, it cuts the x-axis, then it is parallel to y and z axis. So you can mark here, so this is the x-axis, this is the y-axis, and this is the z-axis. So it is cutting this x-axis at a particular length A. So here this is the edge length or translation vector in the along the x direction A. Then it is a perpendicular. It is a cuts the there is no y-intercept and x-intercept. That is it cuts it is parallel to z-axis and z-axis. So OB and OC should be infinity, means intercepts parallel to that axis. If it is 0, 1, 0, then it will be an axis which cuts the B axis, y axis. Y axis it will cut. 0, 1, 0 is here. 0, 1, 0. This axis, this plane is 0, 1, 0. So it cuts the y axis, but it is parallel to x and z axis. 1, 1, 0, it is a cross plane. That is, it cuts x axis and y axis. So xy plane diagonal ആയിരിക്കും. Then 1, 1, 1, all the axis is intercepting. So at the same distance. And so 2, 0, 0 plane, parallel planes have same Miller indices will have the same Miller indices. All parallel planes will have the same Miller indices. 2, 0, 0 plane means it is a plane which cuts the axis at this h value is equal to 2. If h is minus 1, it is represented as a 1 bar. To sketch negative Miller indices, what we have to do is bar 1, 0, 0 we have to cut. So we are taking OA equal to minus A, that is intercept on negative axis. So to draw that, we will shift the origin. So first of all, we were putting here the origin. So instead of that, we have placed the origin here. So that is, so here new origin here. So this will be this is a positive x direction, then this one will be the negative direction. So this plane, the marked plane will be bar 1, 0, 0. Then family of planes, it is enclosed in this type of a bracket. Means a family of planes 1, 0, 0, bar 1, 0, 0, 0, 1, 0, 0, 1 bar 0, 0, 0, 1 and 0, 0, 1 bar. So family of planes is represented by this symbol. Then another problem you can do, find the Miller indices of a plane that makes intercepts on A, B and C axis equal to 3 angstrom, 4 angstrom and 3 angstrom in a tetragonal crystal lattice with a C by A equal to 1.5. So OA is to OB is to OC, that is given as 3 angstrom is to 4 angstrom is to 3 angstrom. Then in this case C by A is equal to 1.5. For tetragonal crystal, the peculiar properties are there. A equal to B, not equal to C. So A equal to B means B is equal to A, C is equal to 1.5 times A. So H is to K is to L is. So you have to divide it with so H is obtained as A divided by OA, B divided by OB and C divided by OC. So A by 3. Then is to A by 4 is to 1.5 is A divided by 3 angstrom. So that is equal to 1 by 3, 1 by 4, 1 by 2. So HKL will be equal to 4, 3, 6. That is the Miller indices of this. So here what we have to do, we have to take the length. So this is the mix intercepts on x, intercepts are this one. Okay, so you have to take the reciprocal here. So we have taken OA divided by A, taken the reciprocal in order to obtain H is to K is to L. So the value of HKL is 4, 3, 6, etc. Now suppose we have to find out the angle between two crystal directions, HKL. The angle between, you have to take notice that it is the angle between two crystal directions HKL in this square bracket. So in the case of cubic crystal, it is H1 H2 plus K1 K2 plus L1 L2 divided by root of H1 square plus K1 square plus L1 square raised to half into H2 square plus K2 square plus L2 square raised to half. Here you have to put one square here. That is the angle between two crystal directions. Then representation of planes of non-Miller indices. First of all, so Miller indices are given and you have to find out the planes. So first of all, we have to take the reciprocals of the given Miller indices. They represent the intercepts in terms of axial units. That is a method. You have to reverse the process of how we have find the Miller indices. The reverse process, you have to find out the representation of planes. Then mark the length of the intercepts on the respective coordinates axis. Join the endpoint. The resulting sketch will represent the required plane.